So what we're wanting to do, or not what I'm wanting to do, is just go through this one more time. And most likely that means the test will not be next week, but the week after, just how the days are falling. Because today we're going to go over least common multiple and inverse, direct and inverse variation. Tomorrow we'll go over addition, subtraction. When we come back from the weekend, we'll go over multiplication, division, and complex fractions, and then solving. So we're going over it all one more time. And then again, I'll give you all another makeup day review, go over the review and test. So we'll have the same full thing for that. And if you do already have the review sheet, go on, hang on to it, because I prefer not having to print off another 50 copies of it if we can avoid it. Now, what we're looking at today first is inverse and direct variation. I think most of y'all like direct and inverse variation because it wasn't too bad. Now, for direct variation, the main equation for it is y is equal to a times x. And we're really just looking at two variables. As one increases, the other increases, or as one decreases, the other decreases for direct variation. Well, really, I can also say that x is equal to a times y. It's the same thing. But it's not so much that we're stuck with y being on one side. We're just saying as one increases, the other increases. As one decreases, the other decreases. So the placement of x and y really doesn't matter. Which also means we did have our other variation saying that a is equal to y divided by x. Really, we can also say that a is equal to x divided by y. And it really doesn't matter how it looks, because if it is direct variation, we'll still get the same a all across the board. But for this one here, if the value of a for the top one was, say, 3, this one here, the a would be 1/3. But it's still a constant number. It's still just a number. So really, any of these here are the exact same thing. They're just different ways to write our direct variation. Now, the same thing is true for our inverse variation, because we're given the general equation, x or y is equal to x over a. Well, that means I can easily say that x is equal to a over y. They're the same thing. They're both still considered inverse variation. And the other way that we had this is that we could get the variable by itself, saying a is equal to x times y. And we have this here. And really, for any of these here, x and y, when they're on the same side of the equation, they're either being multiplied together or divided. They're either multiplied or divided. So if I have x plus y or x minus y, we know it won't be direct or inverse, because direct and inverse variation are really stuck around multiplication and division. So let's go on and look at the first three examples, identifying them as direct or inverse variation. So when we look at a, we have x times y is equal to 5. Well, this here would be inverse, because this is matching up to the general form of x times y is equal to a is equal to a number. And if it helps, we can also try to get it so that y is by itself. And if we did that, well, we would divide both sides by x, telling us y is equal to 5 divided by x, which is still our inverse variation matching up with the form of y is equal to a divided by x. Let's look at the next one, b. It would be neither. The main point is our minus sign. Since x and y are on both sides of the equation, and we have the -4, it's going to be neither. Any questions on A or B? What about C? What would it be? It would be direct. It'd be our direct variation. Now, the different ways we can look at this is, one, we can really consider this as 1/2 times y is equal to x. Because A is, again, just a constant term. The other way we could have looked at it is if we multiplied both sides by 2 to get y by itself. Well, here the 2 and 2 would cancel, telling me y is equal to 2x. Now, if we also looked at all the different versions of direct variation, y is equal to a times x. And our other one is a is equal to y divided x by x, or x divided by y. And whenever x and y are on opposite sides of the equal sign, for direct variation, they're both in what? The numerator. They're both on top of the fraction. Here, x and y are both in the numerator, so this is going to be direct. If they're on opposite sides of the equation, and one of them's in the denominator, then it's going to be inverse. So if we look at number 1 here, 6x equals y would be what? Direct, inverse, or neither? Direct. Because it's coming in the form of y is equal to a times x. And since x and y are on opposite sides of the equation and both in the numerator, we're talking about direct variation. How about number 2? Inverse. Because if they're both on the same side and being multiplied, it's inverse. If they're both on the same side and being divided, it's direct. And if they're on opposite sides with one of them in the denominator, then it would be inverse as well. Number 3, would we say direct, inverse, or neither? Neither. And the big giveaway is the fact that x and y are being added. Because when we talk about direct and inverse variation, we're talking mainly about multiplication and division. And when x and y are on the same side, they're being multiplied or divided, one of the two. Any questions on these here? So let's look at 3 more of these here, and then we'll move on to the next part. So when we look at these here, x times y is equal to 17 would be inverse. How about y is equal to x plus 29? Neither or neither. And lastly, direct. It'd be direct. Now the next thing we looked at, especially when we covered this the first time, was taking sets of numbers, these tables, and determining whether it's direct or inverse variation. And the way we did that is using the equations a is equal to x times y, or a is equal to y divided by x. Make that look more like a y. And if we multiply them together, all of them, the x and y, and we get a constant term for all of them, it's going to be inverse. If we divide y by x for each one and get the same, it is going to be direct. So which one do we think that A is going to be, direct or inverse? Inverse. So we can start off by taking negative 12 and dividing it by 2. And well, negative, yes, multiply, thank you. It's very tempting to say that it's divided. Negative 12 times 2 would give us negative 24. Negative 6 times 4 is, well, negative 24. negative 4 times 6 is negative 24. And lastly, negative 3 times 8 is, so exactly this would be inverse. Because when we multiply, it's talking about the inverse, and when we divide, it's talking about the direct variation, which is very easy to switch the two. And we can also see it with the numbers, because 2, 4, 6, 8, each one of them is getting bigger or farther away from 0. The y values, negative 12, negative 6, negative 4, negative 3, are getting smaller, closer to 0. So they're going in opposite directions. Now let's look at B. Our x values are 1, 2, 3, and 4, and the corresponding y values are 2, 4, 8, and 16. Do we think this would be direct or inverse? Direct, because both of them are increasing, because direct variation, they're either both increasing or both decreasing. So we would be dividing for this here, so we can say 2 divided by 1 is 2. The next one is 4 divided by 2, which is 2. So that's looking very good. Let's go on and finish it out to make sure. 8 divided by 3 is not 2. Well, for inverse, we use, because by definition, if we get the variable by itself, we would use this here, because we're trying to get a by itself. And the direct version, direct variation, is our y divided by x. Because for direct variation's equation, y equals a times x. If we get the a by itself, we get a is equal to y over x. Well, this here tells me the direct variation doesn't work because we need the value of a to be the same for every pair of numbers. Now, inverse, we can go on and check it. 2 times 1 is 2. 2 times 4 is 8. So this here would be neither. Because we don't get a constant term for inverse and we don't get a constant term for direct. Because we need that value of a to be the same all the way across. Questions on this here? Let's look at the next two. So number 4, in the x values, we have negative 4, negative 3, negative 2, and negative 1. For y, we have 20, 15, 10, and 5. So if these are an inverse variation, y times x will give us a constant value of a. If it's a direct variation, y divided by x would give us a constant term a for all of these here. Which one do we want to try first? Direct. Yes. So we're going to do y divided by x. So we can say 20. Right. 20 divided by negative 4, which would be negative 5. Then we do the next one, 15 divided by negative 3, which would be negative 5. Then we would do 10 divided by negative 2, which is negative 5. And lastly, 5 divided by negative 1 is negative 5. So this here would be a direct variation. And it also kind of gives it away a little bit in the numbers. We just have to make sure and check it with the equation. But from negative 4, negative 3, negative 2, and negative 1, the numbers are getting smaller. The values of y, 20, 15, 10, and 5, are also getting smaller, and they're actually getting smaller by the same amount. So it would be direct. Now let's look at number 5. So on number 5, we have the x values of 1, 2, 3, 4, and the y values of 60, 30, 20, and 15. So which one do we think it is? Inverse, because one is increasing and the other is decreasing. So if we multiply the x and y, 1 times 60 is 60. 2 times 30 is 60. 3 times 20 is, well, 60. And lastly, 4 times 15 is 60. So this here is inverse variation. Questions?
How are you supposed to tell the difference? Because you said on this one, if one is going up and one's going down, it's inverse.
Yep.
But on the other one, on the negative numbers, they're going up, and then on the positive numbers, they're going down.
So where are we going? Because if we look at it graphically, the x values, -4, oh, I need to put it underneath. So we have -4, -3, -2, and -1, yes?
Yeah.
And then we have 20, 15, 10, and 5. Well, these here are what? Both of them are decreasing. Because it's not so much the positive we're thinking of, because we have a very strong concept of negative. The smaller the negative, the bigger the number is, which is true. But if we look at the numbers here, well, we're approaching 0, yes? And these numbers here are approaching 0. So really, we're talking about them getting smaller. Not so much in quota. Or here, we're going away from 0. And this here is going towards 0. One of them is going bigger, one's getting smaller. It's not so much in, yeah. Because we have a strong concept of negatives, smaller negatives are bigger. And we look at this one here, 2, 4, 6, 8, these are going away from 0. But these here are going towards 0. They're going in opposite directions. And the issue with inverse is the fact that at 0, for most of these here, it is undefined at 0. Because we're looking at the equation, really, y is equal to a divided by x. Well, x cannot be 0 because we can't have that division of 0. So it's kind of hard to think about it, especially if we're looking at opposite sides of positive and negative. Because if they're both negative, we can see, okay, one's getting a bigger negative, one's getting smaller. So a better way to look at it is probably, where is it going? Is it going to infinity or is it going to 0? Any other questions? So that brings us to the other part, the least common multiple. And least common multiple is trying to see what is the smallest that we can make all of the terms, all the expressions be. So we're going to be increasing them from whatever we have. So if we look at this here, 16m, negative 12m squared n, and 8n squared. So for the 16, 12, and 8, they are going to get bigger, because for the least common multiple, there is a chance that one of them, if we had 3 numbers, that the least common multiple could be one of them, but we know that we'll be at least increasing the others. So we're looking for the first number with our numbers. The first number that's 16, 12, and 8 will all be the same. We're looking for the first number where all 3 of these will be the same. And it would be 48. Because one way we can look at it is by doing the multiples of 8, 16, 24, 32, 40, 48. For 12, 24, 36, 48, and 16, 32, 48. Go this way. And that's the first number that all 3 would be. Okay. Now, here, if we hit math and go over to number, Number 8 in the list is LCM. Now the only downside with this here is it only does 2 numbers. It'll only do 2 numbers at a time. So I can pick 16, comma 12. So I'm asking it to find the least common multiple between 16 and 12. I just picked 2 of the numbers. Enter. 48. So I can do it again. So I can go up and grab least common multiple. But the one that we were missing was 8, yes? And we already found that the least common multiple between 16 and 12 was 48. So if I look at 8 and 48, it tells me that it's 48. So I'm looking at 3 numbers. I can use this twice, and it'll tell me what it is. And they might have that on the ACT, so that might be helpful. So that's 2 ways to go about it. So we would have 48. And it would actually be negative. Yeah, we can. Because since the 12 is negative, to make them all be the same, we need them all to be negative. Because since one of them was negative, the others have to be negative, because we're trying to get them all to be the same. Okay. Any questions on that before we start looking at the variables? Let's look at m first. So in the first one, we do have 16m. In the middle one, we have m squared. And we don't have any m's in the third. What is the most number of m's that appear in any of these here? 2. So to get them to be the same, I need 2 of them. So we would say m squared. Now let's look for n's. Well, the first one doesn't have any. The middle one has 1, and the last one has 2. So how many do I need? 2. So it's going to be m squared. So the least common multiple, the smallest that this will be here, is negative 48 m squared n squared. And that's it. That's all we have to do. And really, we're doing the same thing with m and n that we did with 48. Because the other way to do that is to break it down into prime factorizations and grab the most of each of the numbers. But I think doing this here or doing it in the calculator is a little bit easier. It makes a little more sense. Let's look at the next one here. Least common multiple. 30. In this one here, we don't even really need to, if we use the graphing calculator, do it with 5. Because 5 and 10's least common multiple is 10. Because it's the smallest number it can turn both of those into, and 5 and 15's least common multiple is, well, 15. So really, we're just looking at 15 and 10. Looking at these two here, and well, the first number that they're both going to be is 30. Goes 10, 20, 30, 15, 30. Now we'll go in alphabetical order, so we'll look at X first. Well, the first one has 1x, the middle one has 2, and the last one doesn't have any, so exactly we need 2 of them, x squared. So if we look at y's, first one has 1, the middle one doesn't have any, and the last one has 2, so we need y squared. And if we continue on with this pattern with z, we'll need z squared, yes? No, because how many z's do we have in any of them? So we only need it once. Well, how many y's are here? Here are 2, so the most that it appears is twice. Because if I want to get them all the same here, I just need to multiply it by y once, and now I have 2 of them. So just because it appears in more than one spot doesn't mean I need it more than once. The only time I need it more than once is if it shows up in one of these more than once. So even if one of the others here, I had 10Z instead of with it, well, you'd only still need it once because in any of them it only shows up once. We needed the x squared and y squared because we had 2 of them here and 2 of them here. Any questions on this here? All right, you ready for this one? What would this one be? So we would need an x minus 2, yes. What else do we need? X. As we're trying to make them both be the same, well, to get the x and x minus 2 to be the same, because the x minus 2 is one term. They're stuck together. That is a whole term. So it and x are not the same. So you're going to be the same. Well, I need an x and I need an x minus 2. That's it. So any other questions on this here before we look at the next one? Let's look at this one here. Now in the first expression we have y minus 2 and y plus 2. In the second expression we have y plus 2 squared. Well, really, what is this telling me? That I have 2 times y plus 2. Because whenever we squared, we're saying that we have it times itself. So the y plus 2 is being multiplied by itself. So what is one thing that we know that we need? We need a y minus 2. Because the first one does have a y minus 2, yes? What else do we need? A y plus 2. Because the y plus 2, okay, is here, and we do satisfy this here because we do have 1. Do we need anything else? We need another y plus 2. Because since it appeared twice in the second one, we need it twice. Even though it does appear once in the first, that's fine, but because it occurred 2 times in the other, we need it twice. Yes. We could say y minus 2 times y plus 2 squared. Yeah. Either way would be fine. And that's it. Any other questions on this here? Let's look at the next one. Well, luckily, they do have them all factored for us, so we don't have to factor anything. But looking at these 3 here, what is something we know we need? X. We do need an x squared, yes? Because the middle one does have an x squared, and that also does satisfy the single x we do have in the first one. What else do we need? 2 of the x minus 1s. Or we can say x minus 1 squared. So we would need an x minus 1 times x minus 1 or x minus 1 squared. So having it at least once does cover everything in the first. Having it twice covers everything in the last one. So that there is the least common multiple. And that's all we need to do for this here. Any questions on this? Are you ready for the next one? Okay. This one here would be very tempting to say that the least common multiple is x squared minus 1 and x squared plus 2x plus 1. But that wouldn't be the least common multiple. So this here would not be correct, and I'll show you why here in a second. Because if we look at these two here, x minus 1, can we factor it? Yes, and it would factor 2, x plus 1, and x minus 1 would be the factors of it, because it's a difference of perfect squares. X plus 1 and x plus 1. Now that one there is a perfect square trinomial, and we could have worked it out by factoring it. Since 1 is positive, the signs are the same, and they match the sign of the middle term, which is positive. Well, the only factors of x squared are x and x. The only factors of 1 are 1 and 1, and it does work out to be this here. Now let's see what the least common multiple is. Well, looking at both of these here, what do we know we need for sure? We need an x plus 1. What else do we need? An x plus 1 and an x minus 1. So this here would be the least common multiple. Because the second one does have two x plus 1s, which does satisfy both. And the first one has an x minus 1 that we need. Because x squared plus 2x plus 1 actually does factor to become this. Now, if we look back over to the least common multiple where we wanted to grab the first two, we would actually have been saying that this is x plus 1, x minus 1, x plus 1, x plus 1. Wait a minute. This has an extra x plus 1, which doesn't seem like a big issue, but it will be, especially when we start talking about doing our complex fractions, our complex rational expressions, is it means I'm adding an extra factor of x plus 1 to the top and bottom. That's going to have to be pulled out eventually. When we're solving, it means it's going to have an extra x plus 1 throughout the entire equation, which means if we had ended up having a quadratic, like we saw some of them work out to be, or we had to factor and solve, it wouldn't be a quadratic anymore. It would be a cubic because we added another variable throughout the entire thing. So it increases the degree by 1, which does make it harder to solve. And well, also adds just one of the restrictions, so it doesn't actually help us. So it is very important, especially with these here, to find the smallest one that it can be, so we're not adding any extra factors in when we're trying to solve or simplify. Because I've seen a few of those happen and they get pretty ugly pretty quick. Here, well, t, well, that there is already as simplified as it gets because there's no other numbers with it, and it's by itself, which for our least common multiple, well, I know that I will need a t because none of the others have a t or a greatest common factor of t to pull out, so we'll have just t. Now the middle one will factor. T squared minus 1 is t plus 1 and t minus 1. I put that little hook at the end of the t just so that we can be able to determine and tell it easier from a plus sign. And lastly, we have t squared plus 5t minus 6. Since the 6 is negative, our signs are going to be opposite. Well, the factors of t squared are t and t. Now, we do have two different factors of 6. 6 and 1 or 2 and 3. I would agree it's 6 and 1, and the 6 would be positive and the 1 would be negative. So we already got the t. by itself. What else do we need for the least common multiple? T plus 1 and T minus 1 and T plus 6. And that would be the least common multiple. Because we look at this least common multiple, well, the T does satisfy this here. Having a T plus 1 satisfies this one here, and that's it. The T minus 1 does satisfy both of these here. And the T plus 6 satisfies this here, which actually covers everything. And that's it.
Your attention. I need for the following students to go to the computer lab for the bell ring. This and ours. Thank you.
And that's it. So that's all we are doing with this here for today. So you do have a worksheet that goes along with this here. So you do have 15 problems for this here. The first 8 are determining whether it is direct variation, inverse variation, or neither. If you do have trouble reading some of them, that's understandable. The print on these did not come out well.